Welcome to statics. We have a shear and moment diagram for a beam with distributed loads, and our job is to plot the shear forces as a function of distance and the moment forces as a function of distance across the beam. So let's get started by step number one, which is calculating the external reactions. I suggest you hit pause and do this yourself and make sure you get them right, and then hit resume. So I've drawn a free body diagram over here on the right, and we have a roller at A, so that provides a vertical load. We have a pin at B. There are no horizontal loads, so Bx is going to be 0. And so over here I have a triangle, and so the area of the triangle is going to be 1/2 times the base, which is 3, times the height, which is 300. And so that area is going to be 450. And it would be located at a distance 1 away from A, 1 foot away from A. So I'm gonna for the sake of calculating my external reactions, write down 450 there, and the distance here is 1. Second area to calculate is the area of this distributed load. So I'm going to have the base is 6 feet. I'm going to multiply it by 300 pounds per foot, and so that will be a load of 1800. And I could locate that 3 away from A, 3 feet away from A. So let's go ahead and put that in there, 3 feet away from A, right there. So I have 1800 there. And we're doing this just to find the external reactions. And then that's it. That's all we've got for the beam. And so now we're going to apply the equations of equilibrium to the beam. I suggest we take the moments here at A, because it will eliminate the one unknown of AY. So let's sum the moments at A, set them equal to 0. We get the 450-pound load causing a positive moment. So we write 450 times 1 foot. Now when we think about the 1800-pound load, that will be negative. We'll have a minus 1800. It is 3 feet away from A, so I have a 3. And now I have the moment that By causes, so I have a By. It is 6 feet from A, so I multiply by 6. And when I solve for By, I get, what do I get? By is 825 pounds. And now when I sum the forces in the y direction, set them equal to 0, I have AY plus BY, which is 825, minus 450, minus 1800. And that yields that AY is equal to 1425 pounds. All right. So over here on my free body diagram, I am going to clean this up a little bit and replace it with these values that I know now. So I know that, Bx doesn't matter. And it's no longer going to be useful to me to have these as point loads, because I have to think about them in a more continuous fashion. So as I clean up this diagram, I'm going to have 1425 pounds here. I'm going to have 825 pounds here. And I'm just going to kind of redraw the fact that I have distributed loads. It'll help keep me straight as I work this problem, because I'm going to be plotting them below there. All right, so first step was external reactions. That's done. Second step is break the beam up into similar regions. I see 2 similar regions in this beam. I see a region 1, which is this part of the beam, and then I see a region 2, which is that part of the beam. So we will make 2 cuts. We will cut right here through region 1 of the beam. That will be cut number 1 in region 1. And then we're going to make a second cut here. That'll be cut 2 in region 2. So that's my plan. All right, so let's start with region 1. In region 1, 0 is less than x, which is less than 3. I'm cutting it there, and so I'm going to have a portion of a triangle. And so here's my little piece of beam. I've cut it so I have, and what I'm trying to find out, of course, are what these internal shear and moment forces are. I don't have any reaction load supporting it from the bottom on this left-hand side of the cut between here and here. There's no reaction. There is a reaction at A, but that's not part of our beam yet, so I have no external reactions. And so I do have this distributed load, and so I have to figure out how to treat this. So let's start by defining what X is. I've cut the beam at X. So my length here, or my base of my triangle, is X. And then it always helps me to just draw a little mini triangle. So I've cut it at X. The whole length of the base is 3 feet. The entire height of the bigger triangle is 300 pounds per foot. And so let's label this height here H, and I'd like to find an expression for H as a function of X. And so I can do that by similar triangles. I can say, well, H is to X as 300 is to 3, and then I can say, therefore, H is going to equal 100X. And so, in other words, the height here, right, that height here is 100X. And let me just give that a different color so you can see what I was just doing here. This height right here is 100X. Okay, so now that I've done that, I can now go ahead and write my equations of equilibrium. So let's start by summing the forces in the y direction. This segment of beam is in equilibrium. It is kept in equilibrium by the beam developing internal forces of shear. And so I must include that shear. So I write negative shear because by convention on the left-hand side, you draw it down and you write it in as negative shear. I now have to figure out what my load is. So my load is also going to be negative. So it's the area of the triangle. So I have a half times the base, which is X, times the height, which I just figured out, which was 100X. And so therefore, the shear in this region of the beam is going to equal minus 50X squared. All right, and so if we go ahead and take a look at the beam, at X equals 0, shear will be 0. And at X equals 3, I will have negative 450, I believe. And so what I'm saying is right here at X equals 3, I will have dropped to negative 450, and it ends up kind of looking something like that. And so that's what's happening between 0 and X and 5. All right, and so now we want to go ahead and calculate the moment. We need to calculate this moment. So we do that by applying the equations of equilibrium to the beam again. We're summing the moments at the cut. In other words, I'm thinking about what's happening here. Because shear is going through that point, I don't include it. I do have to include the distributed load from the triangle. So we're in equilibrium. And so I write M, this thing that I'm trying to find, plus, because this will cause a positive moment. So I have the value of that load, which we already worked out was a half times, the value of the load was this much, half the base times the height. So I'm going to write down 50x squared. I've already taken into account the sign here. It's going to be creating a positive moment, so I'm ignoring that negative sign. So I have 50x squared, and now I need to know at what distance from the beam, if this were to be a point load and we were to position it at a particular point, what is this distance from the beam? And so here's my reasoning. Well, if the total distance is x, then 1/3 of the distance will be x over 3. So that little distance is x over 3. And so I am going to multiply it by x over 3. Therefore, m equals minus 50 over 3 x cubed. So let's check. Remember, dm dx should equal shear. In this case, when I take dm dx of this equation, I get minus 50x squared, which matches that, and so that is good news. All right, so over here on my diagram, if I start to plot the moment curve, I get a curve that drops down to, what is that, about 9 times 450. Yeah, it goes down to minus 450. And it curves, so it's doing something like that. That value is minus 450. So that's what's going on in region 1. All right, so let's now take a look at region 2. So I'm looking at the beam, and I have a choice. I always have a choice about which side of the beam I want to take a look at. And so I think it's going to be easier to take a look at the right-hand side of the beam when I look at region 2. So let's go ahead and look at region 2. So what I'm saying is now 3 is less than x, which is less than 9. And so I would like to simplify my life and just think about the right-hand side of the beam. So when you do the right-hand side of the beam, shear is drawn upwards, moment is drawn clockwise. And we have to be pretty careful not to drop any pieces here. So we have this reaction at B. Remember it was 825, so we must include that over here at B. We have to write 825. And then the other thing we have to figure out is this distributed load, right? So we have to come up with an equation to describe it. And so let's remember that x was defined as coming from the origin. It stops there. The total distance of the whole beam is 9, and therefore this distance in the right there is 9 minus x. And so the area of that thing, that region, will equal just 9 minus x times 300 pounds per foot. All right, so let's just kind of keep that in mind. So as before, all we do is we work on the equations of equilibrium. So we're going to sum the forces in the y direction, set them equal to 0. So shear is pointing up now. So I write this unknown shear, which we're trying to find. We write shear. I must include the 825, so let's add that in. And then I need to subtract this area, this distributed load. So I'm going to subtract minus this portion right here. Of 9 minus x times 300. So therefore, shear equals 9 minus x times 300 minus 825. So now let's turn our attention to the moment. Let's take the moment at the cut point of the beam and apply the equations of equilibrium. So the sum of the moments at the cut is equal to 0. So this time, because I'm on the right-hand side of the beam and it's pointing clockwise, I have to write down minus m. That takes care of my unknown. I have to include what's going on with this 825. That's going to be a positive moment, so I'm going to write 825. How far away is it from the cut? Well, it's 9 minus x from the cut, so I'm going to write 9 minus x. And now I have to think about this distributed load. So this distributed load, if we thought about it occurring at a point, it would be occurring at half of 9 minus x. So in other words, it would be this distance right here. Its value is equal to 9 minus x over 2, that distance. So relative to the moment equation that I'm drawing, what I'm saying is that this distributed load may be thought of as a single point force of this value at 9 minus x over 2. So I have the force, which is 9 minus x times 300. It is located at a position of 9 minus x over 2. Okay, let's just solve for m. So what we get is that m is equal to 825 times 9 minus x minus 150 times 9 minus x squared. So let's check. Let's take our dm dx, and it better match what we found. It should be shear, so what do we get? Well, dm dx, it looks to me like we get minus 825. And then what do we get here? 2 times 150 is 300x. And I believe that's positive, because we have the derivative of minus x, which is minus 1, and that counteracts the other negative 1. So that should match what we had found for shear. And if we expand what we had found for shear before, you should find that they match. Let me make sure that that is so. All right, yep, we got the minus 825. dm dx is 300x times 9 minus x. Yep, you know what, I'd have forgotten here. Right here, I have 300 times 9 minus x to the first power. That's what I get here. And now it matches. There we go. All right, so always stop yourself. If they're not exactly matching, stop yourself and convince yourself that either you have a mistake or that you don't have a mistake, but do take the time to kind of sort that stuff out. All right, so now we plot this equation and the shear equation on our curves here. So check for continuity. When you check for continuity in this case, what you're going to find is that it doesn't start at this value. It ends up starting up here at 975. But that makes sense because this difference here is equal to 1425. Why is it equal to 1425? Because it's being held up there with the force of 1425. Over here, the shear equation ends up finishing off down here at minus 825. That makes sense because it's being held up at the very end by an 825-pound force. It's a linear equation, if you take a look at it. So what's happening with shear is it's just doing something like that. So across the beam, we start at 0, drops, the shear value rises suddenly, linearly drops, and then at the very, very end of the beam, there's no shear because it's being supported there. So what's going on in a moment is that we have this equation going on like that, and I have plotted this ahead of time just to save a little bit of viewing time here. So it hits a maximum of about there, and so it's doing something like that. All right, that is the end. So in this segment, we learned about how to deal with a triangular shaped load. And so the only thing new was basically thinking about the height of that triangular shaped load as a function of x. We ended up with a x over 3 term because in our moment equation, and that introduced some, a cubic in the moment, but it's okay. It all ends up plotting out pretty nicely in the end. All right, that's it.